Welcome to section 6.1 quick review. Now we're not really going to focus too much on this chapter because you guys should have had it during physical science, or some of you guys are taking chemistry now, but I just wanted to make sure, in case it was something that you hadn't seen in a while and you wanted to, that you can get a quick overview over the basics of atomic theory and structure that we'll need for biology. So not a whole lot. So starting off the very basics, when we talk about an atom, atoms ultimately have, we'll say, 4 parts. You've got the outside, which this is the old drawing that shows orbits that isn't really true. It's more these clouds. But you've got these electrons that are going to be on the outside of the nucleus. So they're going to be kind of bouncing around, floating around, whatever you want to consider it, outside of the nucleus. That's our electrons. Now the nucleus is the other key part of the atom. This is very small. This is not the bulk of the atom, it's a tiny part of it, but it's most of the mass of the atom is crammed together in this central part. This is not drawn to scale. You know, this would be it'd be a tiny speck if the electrons were being shown that distance away. Now the nucleus itself, having all this mass, it's because it contains protons and neutrons. So these are the other 2 subatomic particles, as we call them. Protons, remember, are what give us positive charge, electrons give us negative charge, and neutrons are neutral. They have no charge, but they do have mass. So that will be important later on when we talk about certain things like radioactive dating. The neutrons will actually play kind of a key role there. So this is the basic structure of an atom. Protons and neutrons in the nucleus, tiny dense part in the center. Then you've got a large part outside of that that's primarily empty space with some electrons flitting around in there. So now we're on to chemical bonding. So chemical bonding is when we take multiple atoms and we stick them together using these things called bonds to form molecules. Right? So this is just going to be multiple atoms together. Now when we want to stick 2 atoms together, there's 2 basic ways we can bond them that we'll ever really see in biology. That's covalent bonding and ionic bonding. Now I will tell you, covalent bonding is by far, hugely by far, the most common one that we're going to see biologically. So this is going to be our main emphasis. And the way this works is you have atoms that want to have a specific number of electrons in their outer energy shell to feel stable. And that number is usually 8. Now, there's one exception, that's going to be hydrogen, who only wants 2. So carbon wants 8 electrons, but it only has 4. So let's just look at these red ones and say the red ones are carbon's original 4 valence electrons. So it needs 4 more to be stable. So what it tends to do is form 4 covalent bonds, where it will share one of its electrons with somebody else who also shares an electron. And so in this case, we've got hydrogen that has 1 electron. He wants 2. So by sharing this electron, by kind of putting it into the pool, carbon also shares 1 electron. So they both look at this region where they're expecting to see their electrons, and they both see 2 electrons. So they're both happy. Hydrogen wanted 2, it has 2. Carbon, by forming 4 of these bonds, looks around and sees 2, 2, 2, 2, 4 sets of 2. It sees 8 electrons. So it says, hey, I'm stable. It doesn't matter that they're being shared as far as it's concerned. Within its electron cloud, it sees 8 outer electrons, so it's content. Just like hydrogen within its electron cloud sees 2 electrons, which is what it wants, so it's content. These are strong bonds. This allows these chemicals to be much more energetically stable, which is a lower energy level, so that makes them what some people say is happier. They don't have emotions, but really what they're saying is it makes them more stable. Now with ionic bonds, what happens is you've got somebody that's so far away from getting an octet, which is the stable arrangement, that their fastest way to get to an octet is actually to ditch the electron that they have, this like 1 outer electron, because underneath that 1 outer electron is a whole nother shell that's full, which is stable. So instead of trying to collect extras to get a full set, they're just like, I can get a full set if I just get rid of 1 or 2 electrons. So in the case of sodium, Na, this guy has 1 valence electron, which is just not stable, so it just ditches it. It just wants to find somebody to donate it to, just saying, take it. And so it donates this electron to somebody who's almost got a full set. In this case, we have chlorine that we're using, but it could be something else, iodide, oxygen. There's lots of guys that, you know, have 6 or 7 valence especially that really want those. And so by giving it that electron, chlorine's now stable, sodium is now stable, they're just ions. So we now have a sodium ion, which is 1 positive because it lost a negatively charged electron, and we have what we call a chloride ion, which is basically going to be 1 negative because it gained an electron. So So then you might be like, well, why are they attracted then? They just donated it. That doesn't mean that you're connected. Well, the charge is what causes this. If you remember that opposite charges attract. So now we've got this positively charged guy that's near this negatively charged guy, so they're going to attract each other. Now, it doesn't have to be this exact sodium. You know, you could have where there's a bunch of sodiums and they kind of shift around a little bit originally. It's not like they have to exactly bind to the guy they donated it to. But you are going to see that these positively charged, we call them cations, are ultimately going to be attracted to these negatively charged anions, and it's going to be a strong attraction. I mean, this is going to be something where they're held together tightly. Now, for biological purposes, though, because you have a positively charged and negatively charged ion, and because water, a substance that we're made up of a lot of, happens to be partially charged, if you put ionic substances into water, they tend to dissociate. That means they break apart, and these ions just start to, instead of interacting with each other, you'll see that these ions start to interact with water instead. And so if you put salt in water, you'll see the salt will dissociate. It'll kind of seem to break apart in the water. So this is why we don't talk about ionic bonds as much for biological purposes, because in most cases when you put ions into our bodies, they tend to just dissociate and kind of spread apart into our body fluids, you know, like blood, etc. So this can be important because we can still move those ions around our body. It can still matter, but they're not normally going to be like in crystallized ionic form inside of our body. There are some cases when they do, things like gout, where you get these crystals that form that are not fun. But that is typically more of a rarity, and it's more of a problem when it happens than the de facto of what we expect. Now, we do have in some cases where we have actual separate molecules that stick together. So this would be like if I've got a series of waters that we're going to talk about in 6.3, but if I have a series of these separate water molecules, each of these is its own separate thing that's covalently bound to each other. So two H's are bound to an O, that's one unit, that's one molecule. But sometimes we'll get where these molecules can weakly attract each other. So that means this one H2O can weakly attract another H2O. And so sometimes they'll show that with like dotted lines to show it's kind of weaker. These are not as strong as chemical bonds, nowhere near as strong. But you can get these attractive forces that help stick together separate molecules. The most common and the strongest of these will be the hydrogen bond, which is misnamed. It's not a bond. It happens to be the strongest attractive force between molecules, but it's still only probably about 5% as strong as a covalent or an ionic bond. So much, 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 much weaker. There's other forces that exist that we won't get into that also kind of help these things stick together, but keep in mind that even separate molecules can actually help stick together. It's just not going to be as strong. It's much easier to separate those guys versus a covalent or ionically bonded substances, which are very difficult to break in most cases. Now lastly, we've got this idea of substances. So oftentimes you'll see this referred to as pure substances. So on Earth, we can find the simplest pure substances are elements. So we can have oxygen, which is oxygen. You know, that's just what it is. It's the smallest we can break something down and still keep its properties. So we call those elements. And there's 92 that we find in nature. There's others that are man-made, but for biological purposes, we normally don't deal with those as much because they're not in nature. And the idea of what makes an element is they have a specific number of protons. So if you look on the periodic table, there will be an atomic number that it's ordered by 1, 2, 3, 4, 5, 6, 7, 8, blah, blah, blah. That's the number of protons that it possesses. If I were to remove a proton from an atom, from an element, it would become a different element. So for identity purposes, just keep in mind protons are what matters. Because we can add or remove electrons, and that's what gives us ions. That's what ultimately gives something charge. Right? I didn't change the protons. There still might be 10 protons. But if I take away 2 electrons, you're now 2 positive. And the reason for that is because you have 10 positive charges, protons, and 8 negative charges, electrons. So if I just do the basic math, I'm 2 positive. So we can add electrons, remove them, and give something charge. We'll also have isotopes that we deal with in later sections. And this is basically where you have the same number of protons, the same number of electrons, but you differ in the number of neutrons that you have. And so this is important when we talk about some radioactive elements, some radioactive isotopes that we use to date things. And then lastly, beyond elements, if we stick multiple elements together and bond them, we know these guys as compounds. So if you've got more than one element bonded together, that's going to be considered a compound, and that's most of the stuff that we talk about in nature, in biology. Most of these things are going to be like water. Water is a compound, H2O. Salt would be a compound, NaCl.